Hello class. In this short lecture video, I am going to introduce the basic circuit theory and how I can relate to the new chapter of this course, the chapter 3. Over the past few weeks, we have touched on the subject that is related to the introductory material and the operation aspect of distribution system under the emergency condition. What I mean by that is the fault occurrence and how the dispatcher coordinate with the crew on site to resume power back to the soon as possible. While we understand that the modeling is crucial, we start to realize that the data preparation or modeling is a very difficult step. Getting the topology data up to date can be hassle, and we have been dealing with the maintenance of the database through GIS, the Geographical Information System. I also mentioned about how fascinating to do this conversion of data from the GIS format to the SCADA system before. So this is an ongoing subject that the dispatcher and the at the control center, they have to constantly doing all this. How about when a feeder is not even there? What are we going to deal with that? Well, and then we also have to decide how are we going to deal with the economic aspect of the short term and long term. Well, in this case, we will need a model that could give us an estimate that evaluate the power loss and voltage profile. As I repeatedly mentioned, these two are the essential part of not just in operation, but also in planning. And what that is, we intend to do. That's what we intend to do in chapter 3. On this slide, I'm going to review a little bit of basic circuit that you probably have learned it already in your sophomore year, just to refresh your memory how the basic concept of how to determine the power loss and the voltage at the receiving end. So as you recall that the power loss would be actually, this is the line that will be expected to be lost, and you have the I square R. So the R here is actually the G line, which is the real part of it. So R, just for consistency purpose, I'm just going to use R plus JX, and that's the part that we will be using a lot for the power loss. So this is a P loss equal to I square R. The voltage profile here, which is a V load, can be calculated from this simple circuit. Is the V load will be equal to V, the sending voltage, multiplied by the ratio of the, for the denominator value, you will have to use the Z line plus the Z load, which is right here, G load, and then the denominator value will be the G load. So this is the way how we analyze in circuit that how to determine the power loss and the voltage profile. So this is number 1, this is number 2. Under these circumstances, it's easy because the circuit is straightforward. It's pretty obvious how we actually can solve it using the basic circuit theory that you learned before. But what is new about this course is that it's going to get complicated when we include a lot of load, not just one, but many. So what I mean by many is you are not just as shown in this picture figure. Not only one load, you have multiple load along a distribution feeder. As I mentioned, for simplicity, we are only just considering this arrow as a load for any distribution transformer. So you have 1, 2, 3, 4, 5, 6 distribution transformer is regarded as a load. And then this is a load profile you will be observing over the distance. So this is a L with respect to distance from the feeder head all the way to the feeder end. And as you can see that the voltage at the substation level is usually close to nominal value, which is 12.47 kV, just like the voltage value we had at Michigan Tech substation. So the value of the magnitude, so this is the voltage magnitude. So it will drop along the feeder, but sometimes if you want to improve the profile, say if you want to maintain this profile throughout the entire feeder, There are two ways to improve the voltage profile here. So one way is to insert a capacitor here, which is shown as number one option, that will shift the entire blue curve all the way up upward so that will be the red color shown in this picture. So this is not a very good drawing, but you got my point here. So in the end of the last video, the load, the voltage of that last load will still fall between the range that you desire to be, to want that to be. The second option is to place a regulator somewhere along the distribution feeder, so that as shown in the green color, that it will be abruptly shifted up and then go down again. We usually see this regulator installed in the rural area because of the much longer distance of distributing power. The difference between the two, capacitor and the regulator, is that the capacitor will correct power factor, whereas the regulator doesn't. So as you can tell, this abrupt shift of voltage will actually also proportionally the same way abruptly shift current down for this that start at this point of the distribution feeder. So this is a simple case with a multiple load one feeder. As you know that the complexity of a distribution feeder is beyond just 5 distribution transformers. So to be realistic, you have to come out with a way to assume what would be the number of customer at a given coverage of area, and that sort of motivate us to further investigate the kind of coverage of shape that we will be using to determine power loss and voltage profile. So in my next figures shown here is that, so we start with this feeder head x equals 0, whereas we originally put 2 dots here just because we had 2 load here. But as I said before, realistically, we're going to have to include multiple load point along this lateral. So that means that if we're going to expand this lateral toward to the east, then it will become the shape like this shown here. So this shape is a rectangular shape that we will be interested to determine what will be the voltage profile, and then what will be the power loss. So nothing has changed so far in terms of objective. What we are interested is to presume if we're going to build a distribution feeder which is not even there, how much the power loss will be, what will be the regular normal voltage profile, so that we're going to see if this engineering judgment is wise for investment, given that if you have other parameters that you will be using to find out the cost and mid-term, long-term implication combined. So our interest in this chapter is to have 3 different shapes determined, and the way how author organize the text will start with a Z-lam load geometry configuration, and then it begins the rectangular, triangular, and trapezoid. I sort of want to do this in a different way, so I flip this around. I start with this shape first, and then we'll come back with the lam load and geometry configuration. So in this case, we're going to talk about voltage drop, right? Like you learn from the circuit, if you don't find out the voltage drop from here to here, you can use the voltage divider as I shown before, or you can, if you know the current here, the current from the source, then you can simply using the current multiplied by the Z, that give you the difference of the voltage between these 2 points, right? So that's a small incremental drop, and then you use this small incremental drop using this voltage source minus this incremental drop, that give you the voltage at the receiving end. So same thing here is that we have to do the calculation based on the distance. So you have the as I usually use the breaker as a sending end, and that's from the standing end all the way to the receiving end load, then that's denoted by length L. So usually impedance information is given in impedance ohms per mile. Z plus equal to R plus JX, the resistance and the reactant. So the total impedance will be, you have to multiply this number by the length, because total impedance is really determined by the total the distance from the source all the way to the end. So we have to multiply by the length, and that's how we get into the voltage drop current multiplied by length. Factor L out from the real and the imaginary part to this, and then we will have to use this as the calculation. So as you can see, this is the source, receiving, and then you have the impedance, total impedance. So basically it's the V source minus the VD that give you the receiving end voltage. I can start with a example to illustrate this concept. So example, for the total feeder impedance from this feeder head all the way to the load, you have Z12, which is already given in ohm. So in this case, we are not going to worry about multiply by length, because this is already in ohm unit. So to find out the voltage drop from here to here, the delta, which is pretty much the Z12 multiplied by the I12, equal to 21.65 here. As you can see, the reason why I always encourage you guys to get a graphing calculator is that you have the information, mixture of information is given in polar form here, from the current, and then the rectangular form from always a rectangular form from the impedance. So if you want to go through the math, that's your call, but having a good calculator that will enable you to plug in and find out the information for the voltage drop, for in this case, it will be a few second kind of task that you can do from by using that. So that's the time that is always good to invest a good calculator to determine the value of this multiplication, addition, division, or subtraction for between these complex numbers, and whether or not in rectangular or polar form. So the next thing I want to introduce is the K factor for voltage drop, and the reason that they use K factor is to determine sometimes they have that kind of information from the material to determine the percentage voltage drop per mile per kilowatt load. So if you have the K factor here, that will make the life a lot easier. As you can tell, this information can be given to you, or you have to derive it. So from this example, we're going to say how we're going to calculate the K drop factors, right? So example 1, with a 12.47 kV feeder with 1 kilowatt load and the impedance information equal to 0.306 plus J 0.6272 ohm. To find out the K factors, the first we have to find out is the complex power, which is S equal to a voltage drop times the current, and then the three phase. So and then usually this voltage is given is a line voltage, so we have to divide it by square root of 3, and since we are dealing with three phase, so we will have to multiply by 3. So this is a typical equation you see in power engineering, the square root of 3 times the voltage magnitude and the current magnitude. So to reorganize this a little bit and to determine the current, because we don't know the current, and the current will be equal to the complex power divided by square root of 3 times V. So we know the voltage, we know the complex power, the current can be obtained directly from this calculation, which is 0.463 amp. So now we have voltage, we have current, and to find out the K drop will be simply the voltage drop divided by voltage line to neutral, which is the phase voltage, right? So to do that, it will be the real part of the voltage drop difference, which will be 0.463, which is the current, multiplied by the voltage value, right? I'm sorry, this should be the Z value. So the Z value, so you have the current multiplied by a Z, which is already given. That is 0.306 plus J 0.6272 ohm. So that that voltage drop, real part of the voltage drop divided by the line to neutral, in this case will be 12.47 kV divided by square root of 3.